So in the last class, we introduced the phenomena of electromagnetic induction, and we introduced Faraday's equation describing electromagnetic induction. And actually, the discovery of induction and the equation describing induction are a huge scientific technology windfall for us. So they led, as I've mentioned, to the joining together of electricity and magnetism. That was a huge science event. And they've led to the development of all our modern technology, electrical generators, electrical motors, and much more. So that was a huge technological advance. Today, I want to talk about two examples of induction and Faraday's law that involve motion, movement. And they're both examples or illustrations of what we call electrical generators. Electrical generators are electrical or induction devices that turn mechanical movement, into electrical currents, electrical potentials. So they're turning mechanical energy into electrical energy. And that's very valuable. So we're going to talk about an electrical generator that involves translational motion. That's going to be our first example. And then we're going to talk about an electrical generator that involves rotational motion. That's going to be our second example. The first example involving translational motion is one that's kind of more of scientific, intellectual interest. It's not that practical. The second one, involving rotational motion, is also technologically very interesting. It's very practical. And so we're going to meet these two generators. We're going to meet two new equations that describe each of the generators. I've just listed them here. I'll say more about them later. So there's one equation for the translational motion generator, second equation for the rotational motion generator, and we're going to talk about those as we walk through the class. Okay, I want to make an interesting point about Faraday's law, because it's really a very interesting equation in physics. So it's a very sort of broad equation, very general equation. It just says that you get an induced EMF when you have a changing flux, changing magnetic flux. So it's a very broad, general statement that a changing magnetic flux will create an induced EMF, an induced current. There are two distinct effects, two distinct phenomena that we're going to talk about today and Thursday that can create an induced current, induced EMF through Faraday's law. One is when you've got motion, movement, changing the flux, and that's called motional induction. The other one is when you don't have motion or movement, you just have changes in time causing the change in flux, and that's called transformer induction. And so we're focusing today on motional induction, next class on transformer induction, and both of those have led to our modern technological lifestyles. Okay. Let's actually get on with the class. And let's talk about induction through translational motion. And so this is the situation that we're going to be thinking about. This is the setup that we're going to be thinking about. So let me just describe this, and then I'm going to demonstrate this, demonstrate how this is an electrical generator. So in this setup here, I've got upstairs here is a metal rail, and downstairs here is a metal rail. And I'm pushing this metal rod along the metal rail from the left to the right. And I'm actually completing a circuit with the rod and the upstairs and downstairs rails with this, this wire and resistor arrangement here. So I've built a complete electrical loop. I've built a complete electrical circuit with the moving rod, the rail upstairs, the rail downstairs, and the resistor. This arrangement I've immersed in a magnetic field. So those green crosses are indicating a magnetic field that's immersing this whole setup. And if you remember, the crosses mean that the field's going into the screen. So this is an arrangement, if I'm moving the rod along the rails, that actually creates an induced EMF. It creates an induced flux, induced current. It creates an induced EMF and current because the flux, magnetic flux through the loop, as you can see, is going to change with time. It's going to grow with time as the rod moves left to right. With time, there's more and more field lines passing through the circuit, passing through the loop that is the electrical circuit. And so that's going to create an induced EMF, going to create an induced current. So I'm going to show you that, an example of that. So this arrangement here is exactly the arrangement that's on the overhead, on the screen. These 4 blocks are powerful magnets, powerful permanent magnets. And from those magnets, I actually don't know whether the top is the North Pole and the bottom is the South Pole or vice versa, but either field lines, we can't see it, but field lines are pouring out of the magnets through this region between the rails, or pouring in this region between the rails. Okay, so then I've got a rod, a conducting rod that I can move along the rails, and I will move it along the rails. And then, so that looks like this circuit up here. And then in place of the resistor and the 2 wires at the end of the rails, I've got, these 2 wires, the black and red wires, and I've got this voltmeter. So this is going to tell us, this is going to indicate to us an induced EMF. And so I'm just going to push the rod along the rails. And if you watch the needle, you'll see it deflect a little bit. So it deflected a little bit towards the right there. If I'm going to move the rod backwards, and it deflects a little bit towards the left. And so what is going on here? What is going on is I'm turning mechanical motion, so I'm moving the rod, exerting some force, into electrical currents, electrical potentials, electrical energy. So this is, it's not a very practical one, I admit that, but this is an electrical generator. This is the principle on which electrical generators work. This is how electrical generators work in a power station. They turn motion, movement, into electrical energy, electrical power, and that's what I'm doing. I'm turning my own work done, my own power, into electrical energy, electrical power. And so this is a generator. And so we're going to explore this, how this works, as an example of a basic electrical generator. Okay. So as I move the rod left or right, I'm changing the flux, I'm inducing an EMF, I'm inducing a current. Here's Faraday's law. For this particular generator, this particular arrangement, this particular situation, you can write that rate of change of flux by this little formula here. So this is the new bit here. This says that the rate of change of flux is the magnetic field times the length of this rod here, the distance between the rails, times the velocity that you're moving the rod. So let's think about that equation. I'm not going to show you how I got that equation, but I'm going to not argue, I mean, I'm going to defend, not really defend either, defend that equation, argue the ingredients in that equation. So that equation is saying that the rate of change of flux and the induced EMF, induced current, is in proportion to the product of the field and the length of the rod and the velocity you're moving the rod with. Does that all make sense? Well, let's think about the field. Does it make sense that it depends on the field B? Look, if I had a stronger field, I'd have more field lines passing through the circuit. And so when I move the rod up and down the length of the rails, I would have more changing flux in the circuit. And so it does make sense that the rate of change of flux, or the induced EMF and induced current, depends on the magnetic field. For example, if I turned off the magnetic field, if I had no magnetic field, I could have no induced EMF, no induced current. So it makes sense that the rate of change of flux is proportional to the magnetic field. What about the velocity? Does it make sense that the rate of change of flux is proportional to the velocity of the moving rod? Well, look, if I move it slowly, I'm barely changing the flux through the loop. So I would expect, if I was moving it slowly, to get only a very small EMF, induced current. If I move it quickly, then I'm changing the flux through the loop or the circuit very quickly, rapidly. And so I'd expect to get a much larger induced EMF, induced current. So it does make sense that the rate of change of flux and the induced EMF and the induced current also depends on the velocity that I'm moving the rod with. For example, if I didn't move the rod, right, then there would be no change in flux, and I would get no induced EMF, no induced current. So that makes sense too. What about the length of the rod? This equation also depends on L, the length of the rod. Does that make sense? Well, imagine if I push the rails together closer and I use the shorter rod and moved it up and down. As I move it up and down, then I'm changing the flux through the circuit, but it's over a smaller area. So I'd accumulate less field lines. If I make the rod's rails further apart, much further apart, and have a longer rod, as I move that rod up and down, then I collect more field lines for the larger length rod. So it does also make sense that the rate of change of flux, or the rate of change of field lines through the circuit, depends on that separation between the rails, depends on the length of the rod. If I've got a big separation between the rails and long rod there, I'm going to get a large rate of change of flux, large induced current, large induced EMF. If the rails are close and the rod is short, then I'm going to get a small induced current, small induced EMF, small rate of change of flux. If the rods were right next to one another and the rod had no length, I'd change the flux by nothing. And so I get no induced EMF, no induced current. So all that makes sense. So although we didn't actually formally derive this equation, we actually did something that's much better. We argued that it makes sense, physically sensible, that the induced EMF depends on this product of B, L, and V. Okay, let's look at an example calculation involved in this. In this problem, we're moving this rod along the length of the rails, and we're told some details. The circuit's immersed in a perpendicular 0.3 Tesla magnetic field. There's an induced current due to an induced EMF that is 8.5 milliamps. So we're being told here how much current is being induced. And we've been told that the circuit has a resistance of 9 ohms. So we could also figure out how much EMF is being induced. And then we're going to go off and we're going to calculate the rod speed to create that induced current, that induced EMF. We're going to calculate the force that needs to be applied to move the rod at that speed. And we're going to calculate the power that whoever's moving the rod is supplying to the circuit and the power that is dissipated in the resistor in the circuit. So we're going to calculate a bunch of things here that will expose us to the details of how this generator is really working and what's going on in this electrical generator. So let's see if we can answer these questions. I think I'm going to do this on the device I can't remember the name of. Okay, here we are. And of course, because I'm always anxious, I've started the problem ahead of time. So here at the bottom and here at the top are the rails. Here is the rod that I'm moving with some speed v. Here is the resistor that completes the circuit. So this entire loop is an electrical circuit. And I've added to my sketch the quantities that I was told in the problem. So we were told the length of the rod, the magnetic field, 0.35 meters was the length of the rod. The field was 0.3 Teslas. We were told the resistance of the resistor in the circuit was 9 ohms. We were told the induced current in the circuit was 8.5 milliamps. And I actually wrote down, this is called anticipation. I anticipated I would need this. I wrote down what the induced EMF is. Look, if you know the induced current, you know the resistance of the circuit, Ohm's law tells you the induced EMF. And so I just multiplied I, 8.5 milliamps by 9 ohms. I got 76 millivolts. That's the induced voltage. Okay. So the first thing we're asked to calculate is the speed of the rod. So this is an important point about this arrangement, right? You're only going to get an induced current. You're only going to get an induced EMF if you're moving that rod. And the faster you move that rod, then the bigger the induced EMF, bigger the induced current, and the slower you move it, the smaller the induced current in EMF. So let's start with the relationship between the speed of the moving rod and the induced EMF. It's this one here. I put the little vertical lines around the induced EMF because I'm not going to worry about the sense of it right now. We'll talk about the sense of the EMF or the direction of the current when we move on to the other parts of this problem. But for now, I'm just going to worry about the speed. Well, if I look at this equation, right, we know how to do this. If we want V, the speed, we can just divide through by the magnetic field and the length of the rod. We know those quantities. And that speed will be the EMF divided by the B field divided by the length of the rod. Every one of those quantities I know, right? So I've got a 0.076 volt induced EMF. I've got a magnetic field that's 0.3 Teslas, and I've got a length of the rod that's 0.35 meters. So if I plug them all in my SI units, I calculated 0.73 meters per second. So about 3/4 of a meter per second. So that wasn't too bad. The second question is an interesting question. It says, what force did I apply to move the rod at that constant speed of 0.73 meters per second? So you might be thinking, well, you know, how am I going to calculate that? Why do you even need a force to move the rod at constant speed? The reason that you need a force to move the rod at constant speed is because your force, I'm going to call that the applied force, my applied force has to overcome another force, a second force, that's appeared for the moving rod. The second force for the moving rod is a magnetic force. So in this situation, if we could picture the forces, there would be a magnetic force that is acting towards the left, and I'm, in moving the rod, overcoming or counteracting that magnetic force with my applied force towards the right. And so there are actually, in this problem, a pair of forces going on if you're moving the rod at constant speed. There's a force that you're exerting in the direction of the rod, and there's a force that's opposing that motion opposite the direction of the rod. So the question now becomes, I mean, I've told you there's two forces, but why is there that magnetic force? Where did that magnetic force come from? That magnetic force came from the fact that we've got an induced EMF, we've got an induced current, we've got an induced current that's flowing through a magnetic field, and a current in a magnetic field in general creates a magnetic force. So the magnetic force is a force due to the magnetic field present in the problem on the induced current itself that we've created. To figure out the direction of the figure out the direction of the magnetic force, we need to know the direction of the current. And to figure out the direction of the current, we're actually going to use Lenz's law, which is part of Faraday's law, for the electromagnetic induction. So I've indicated that this current is towards the left, and then we're pushing towards the right. But I'm going to show you why that current is towards the left. So if we look at this sketch up here, we've got a magnetic field that's in towards the screen. Right? The field lines are going in towards the screen. So the induced current will create an induced magnetic field that will oppose that change. The original magnetic field through the loop is there's more and more field lines that are going in towards the screen. So the induced current is going to make a magnetic field that's out of the screen to try and oppose that. So that's Lenz's law. Whatever change of flux is going on, says Lenz's law, the induced current will try and oppose that change. So if the flux in towards the screen is increasing as we move the rod along the rails towards the right, then Lenz's law says that the induced current is going to flow in a direction that will try and oppose that change. So the induced current is going to make a magnetic field, induced field, that's going to come out of the screen towards you. So I'm going to use a right-hand rule. I'm going to point my thumb in the direction of the field that the induced current is creating. And my fingers will naturally curl in the direction of the resulting current that's flowing in the loop. And so if you look, they're flowing counterclockwise around that circuit. And so by Lenz's law, what we figured out is that the induced current, which we knew the strength of, it's flowing counterclockwise around the circuit. So on the right here, it's flowing up, and on the left here, it's flowing down. It flows right to left across the top and left to right across the bottom. So, if the current is flowing that direction, then we can figure, and it's immersed in a magnetic field, we can figure out the force that's exerted on the moving rod. What you do is you point this is the second right-hand rule, you're going to point the palm of your hand in the direction of the current. So for the moving rod, it's going up. You're going to curl your fingers in the direction of the field that it's immersed in. That's a field that goes in towards the screen. And then your thumb points in the direction of the force, the magnetic force. And so you see the magnetic force is towards the right. Is towards the left, sorry. And so this particular current that I sketched that goes counterclockwise creates this force towards the left in this magnetic field that's in towards the screen. And so all of that Maybe I'll write it down. That was a kind of a mouthful, I know. There's other expressions for that, but I won't use them. Lenz's law said the current was counterclockwise, anti-clockwise. Then we found that the magnetic field is towards the left by the right-hand rule for the force law, for the magnetic force, right-hand rule. And then finally, that tells you that our force, the applied force, must be counteracting that magnetic force. It must be acting towards the right. And so that was a whole sequence of arguments that have told me that I need to push towards the right to overcome a magnetic force towards the left, because the induced current is creating a magnetic force because it's bathed in a magnetic field. Okay. So now we've defended the sketch, right, with the magnetic force towards the left-hand side and the applied force towards the right-hand side. And now we just want to calculate the size of the magnetic, my force, the size of the applied force. So the size of my applied force, I'll put the vertical lines around it again, is going to be equal to the size of the magnetic force. They're equal and opposite. And the size of a magnetic force on an electrical current, if you remember from an earlier class, probably like lecture 11 or something, it's the product of the magnetic field, the current flowing in the straight wire, the length of the straight wire, and the sine of the angle between the direction of the current and the direction of the magnetic field. Now, in this case, the current is flowing upwards in the rod. The field is into the screen. So this is sine of 90. This is just 1. And so if I want the magnitude of the force, my force, which is the magnitude of the magnetic force, all I have to do is fill in B, I, and L. So the calculation becomes quite straightforward. So B is 0.3 Tesla. I, the current, was 0.0085 amps. And finally, L, the length, that's 0.35 meters. And if you multiply all of those things together, I got 8.9 times 10 to the minus 4 newtons. That's the force. Except it's fallen off the screen. Okay, so that was a big step, right? We understood that once we've induced the current, induced an EMF, that current is going to experience a force in the magnetic field that the setup was bathed in. And to move the rod, we're going to have to overcome that magnetic force with our own applied force. And we were able to argue with Lenz's law and right-hand rule, the direction of the forces. We were able to argue with the magnetic force law, the strength of the force that we needed. The last part of the problem asked us to calculate two further things: this power that my force is supplying to the arrangement, and the power that is being dissipated in the resistor, in the circuit. So, when you exert a force, you do some work. When you exert a force, you do an amount of work that's force times distance. When you exert a force, you're also exerting power. That's the rate at which you're doing work. And the expression for the amount of power a force is transferring is not force times distance, it's force times velocity, if you remember. So if I take my force, my applied force, and I multiply it by the velocity that I'm moving the rod at, that's how much power I'm transferring to the arrangement, to the rod. It's how many joules per second I'm transferring. It's the energy I'm inputting into the arrangement. And so I am, with this force, this applied force, I'm supplying some power. I'm going to call it P subscript S for supplied power. And it's going to be equal to my force times the speed that I'm moving the rod at. And so this is a equation. You might have forgotten this, perhaps, from Physics 211, but it is an equation that you probably met when you talked about work, when you talked about power, when you talked about forces doing work and transferring power. And so all I got to do is fill in the size of the force, 8.4 times 10 to the minus, sorry about the handwriting, multiply it by the velocity, 0.35 no, ridiculous, going nuts. Multiply it by the velocity, 0.73 meters per second. And I got 6.5 times 10 to the minus 4. And that's watts. That's joules per second. That's the amount of rate at which I'm supplying energy with my force. So, you know, I had to do something. I had to transfer energy when I move the rod to and fro. And this is the rate at which I'm transferring energy if I'm moving the rod constant speed. The other thing we were asked to calculate was the power dissipated, so I call this P subscript D, in the resistor. So this is, we've met this in before test 1. So we've also forgotten that too. But the power dissipated in a resistor is I squared R. Current squared times the resistance. At least that's one way you can calculate it. That's what I'm going to use. So the power dissipated in the resistor is I squared R. This is the induced current, which we know. We were told it. Is 0.0085 amps. And I've got to square that. And then I've got to multiply it by the resistance. We also know that. That's 9 ohms. And look, here's a bit of magic. If you calculate this number, it also is 6.5 times 10 to the minus 4 watts. And those two numbers give us a sort of real picture, mental picture of what's going on in this arrangement, right? What's going on from the perspective of energy in this arrangement is as I move the rod to and fro, I'm supplying energy. I'm doing work. So power is going in from me. That energy that I'm supplying, that power I'm supplying, doesn't just get lost. No, becomes electrical energy, electrical power in the current flowing around the circuit. And finally, that electrical energy, electrical power gets dissipated in the resistor, turned into thermal energy, turned into heat. And through that path of I put in some power, did some work, the electrical current, there's some power, there's some electrical energy, and then there's finally thermal energy and thermal power. No joules of energy was lost. Energy was conserved. So the power in is the power out, and that's a feature of energy, and energy conservation. So it's an interesting way to picture what was going on. Okay. So what we just made is an electrical generator, like a battery is an electrical generator. In a battery, that's on the left-hand side, in a battery, chemical energy inside the battery is turned into electrical energy, electrical power, so that the current can flow around the circuit to create the voltage that's applied to the circuit. In an electrical generator, mechanical energy, moving energy, is turned into electrical energy, electrical power, so that the current can flow around a circuit, so that there can be an EMF induced in a circuit. So although these two pictures look very different from how we've made the EMF, how we've made the currents in the two cases, in both cases, you're turning one source of one form of energy, chemical energy or mechanical energy, into electrical energy, electrical power. And so on the left is how electrical generators work in power stations, and on the right is how your 1.5 volt battery works in your TV remote control. So they're both using other forms of energy, converting other forms of energy into electrical energy. Okay, let's talk about induction with rotational motion now. So here's a classic example of induction with rotational motion. This is a sort of simple example of how an electrical generator in a real power station actually works, actually creates the electrical currents, the electrical power you use. So if you look at this sketch here, we've got a region of magnetic field. So I've arranged a north pole upstairs here on the left and a south pole downstairs here on the right. And the north pole field lines are coming out, and the south pole, the field lines are heading in. So there's a region of magnetic field here. I've got a coil of wire. Now, this could be one turn. Looks like one turn in this picture, or it could be many turns. And I'm not going to translate that coil of wire. I'm going to rotate that coil of wire. I'm going to twist that coil of wire in this magnetic field. Just imagine it. Just imagine you got hold of the ends of this coil of wire, and you rotated them around and around and around and around. What's going to happen? As you rotate them around and around and around, the number of magnetic field lines that are passing through the loop is going to change. If the coil is kind of standing vertically, if its plane is standing vertically, you're going to get a lot of field lines passing through the coil from the north pole on the left to the south pole on the right. If it's horizontal, those field lines are not going to pass through the loop. They're just going to go above or below. And as you turn it around, you keep changing the number of field lines that are passing through the loop. So in the last example, we changed the flux through the circuit by moving the rod along the rails. In this example, we're going to change the flux through the circuit by just rotating the loop. And so as this loop rotates, you're going to have a changing number of field lines through the loop. You're going to have a changing magnetic flux through the loop. You're going to have an induced current in the loop, and you're going to have an induced EMF in the loop. This is how we're going to turn mechanical energy, inputting kinetic energy, into electrical energy, outputting electrical energy. I got a little demonstration of this. Let me show you that. I'll put it on the camera for this because it's a little hard to see. Okay, so let me explain this setup. I've got a power supply here because I'm not using a bar magnet, a north pole bar magnet and a south pole on a bar magnet. I'm using what we call an electromagnet. It's a magnetic field that's generated by electrical currents. And these coils here, the big one at the front and the big one at the back, are like the north and south poles in our sketch here. So just think of them this way. Here's the north pole, here's the south pole, and between the north pole and south pole are running lines of magnetic field. Of course, we can't see the lines of magnetic field, but they are simply flowing away from you towards me between these two poles, these two coils. Inside this region of magnetic field, I've got a loop of wire. So I think you can see that on the screen, I hope. And it's actually not just one loop of wire. It's many, many, many turns of wire. And of course, the reason why it's not one loop of wire, it's rather many turns of wires, you want to get the largest induced EMF. You want to get the largest induced current if you're going to make a electrical generator. If you just have one loop of wire, it's just the number of field lines and the rate that they change going through that single loop. But if you have n loops of wire, then those field lines are going through the n loops. And so you get an n times bigger induced EMF and n times bigger induced current. So it is many, many turns. I think there's like 1,000 turns in here or something like that. And so over here, finally, on the right-hand side, I don't have the lamp that was in the original picture, but this is just or a resistor. This is, again, a voltmeter. And I think you can see or a current, this is a current meter, so it's going to measure the induced current. And you're going to watch that needle as I rotate the coil. And you're seeing that's hot. You're seeing the induced current, the induced EMF that's created by the changing flux, the changing number of magnetic field lines that are passing through the loop. If I move it slowly, you get less induced EMF, less induced current, because the rate of change of the magnetic flux is less. If I move it fast, you get much bigger induced EMF, much bigger induced current, because the rate of change of the flux is much greater. If I don't move it at all, there's no induced current, no induced EMF, because there's no change in flux that's happening. And so this is how you build an electrical generator. Oh, what am I doing? Just like for the generator based on translational motion, we could write a specific equation for the induced EMF in terms of the motion there, the translational motion, V there. For this generator that's based on rotational motion, we can write a specific equation for this type of generator that tells us the induced EMF in terms of the rate of rotational motion. That would be an angular velocity. We call it omega. And that's this equation here. So here's Faraday's law again that said the induced EMF is the rate of change of the flux. And then here we've tailored it to our specific source, origin of change in flux. Again, I'm not deriving this equation for you. I'm doing something that's much better than that. I'm going to argue why the equation looks like this. Why does the equation say that the induced EMF is n, the number of turns, times b, the magnetic field, times a, the area of the loop, times omega, omega's the angular velocity, times this sine omega t factor? Why all that stuff? Okay, let's start arguing it then. Obviously, the magnetic field, right? The stronger the magnetic field, when you rotate the loop in it, the greater the rate of change of flux. So it makes sense that it depends on B. If I turn the field off, you get no rate of change of flux. If I double the field, then you'd be doubling the rate of change of flux through the loop. So it's proportional to B. So that's the B here. Also depends on N and A. Those are properties of the loop, right? If you make a big loop and rotate it, it's going to collect more field lines. And so the number of field lines is going to change more quickly passing through the loop. If you make a tiny, tiny loop, it hardly collects any field lines. So when you rotate it, you don't get a change of many field lines. So you don't get a very big change of flux. So it makes sense that the area, big area collects more field lines, collects a greater rate of change of field lines. Small area collects less field lines, a smaller rate of change of field lines. It makes sense it depends on A. Also makes sense that it's going to depend on how many loops of wire. If you have one loop of wire and then you add a second one, you've doubled the rate of change of flux because you've doubled the number of loops. if you add 3 loops instead of 1. You're going to triple the number of loops. You're going to triple the rate of change of flux. And so it makes sense that the induced EMF also depends on the number of loops. So B, the magnetic field in NA, makes sense. What about the omega? Well, that's the key thing, right? If you don't turn the loop, if omega is 0, the angular velocity is 0, you're never going to induce an EMF. You're never going to induce a current. So it's going to depend on how fast you rotate the loop in the magnetic field. The faster you rotate the loop in the magnetic field, the greater the omega, the greater the rate at which the flux will be changing, and the greater the induced EMF, and the greater the induced current. So all these dependencies, N, B, A, and omega, they all make sense. Increase any one of them, and we would expect the induced current, the induced EMF to grow. Decrease any one, you'd expect the induced EMF, the induced current to shrink. And so this equation makes sense here. There's this extra piece, sine omega t. So that actually, if you think about this equation, compare it to the previous equation with the translational motion. In this equation, the induced EMF is a function of time. In the previous equation, it wasn't a function of time. As long as I move the rod at uniform speed, I got a constant induced EMF, constant induced current. In this case, if I rotate the coil at constant angular velocity, omega, I get a time-varying, a time-dependent electrical EMF, time-varying induced current. And it varies according to sine omega t. So it looks like this if you were to sketch it out. The maximum value is that MBA omega that we argued. So it's at a maximum value here. But it's also, in terms of the size, it's at a maximum magnitude down here. But there are moments when there's no induced EMF. These points here, these nodes here, where the brown line representing the electromotive force as a function of time is crossing the horizontal axis. At those spectral moments, there's actually no induced EMF. So an interesting thing about this generator is that as you rotate the coil, the field, the flux through the coil is not just constantly changing at the same rate. Sometimes it's changing quickly, and sometimes it's barely changing at all. So when the loop is horizontal in here, that's actually when the field is changing quickly. So that's when you would be going from, supposing you're just above horizontal like this, you've got field lines that are passing this way through the loop. As you rotate this way, they're going to start passing the other way, in the other sense, through the loop. So there's a bit, when the loop is horizontal, you get a big change in flux. That's the peaks here. Here, here, downstairs here, and downstairs here. When the loop is vertical, right, that's where you basically collected all the field lines that can possibly pass through the loop. And as it moves around the vertical, it really barely changed that. So when the loop is vertical, that's where the flux is barely changing at all. And so there is where you get almost no induced EMF, these points here on the horizontal axis. So that's a very different feature of this rotational generator compared to the translational generator. This one's creating a sinusoidally varying, an oscillating electromotive force, induced electromotive force. The translational motion example, just as long as you could push the rod constant velocity, it created a constant induced EMF, constant induced current. Here's a little more detailed explanation of this. I just wanted to mention this. It's these portions of in this picture here. So this is kind of a cross-section through the three-dimensional drawing here. Here's the magnetic field that's running left to right. Here's a sort of profile or cross-section view of the rod the coil that we're rotating. Here's the rotational motion, the angular velocity omega. It's this arm upstairs here that's going into the screen, this arm downstairs that's coming out of the screen. These are the ones that create the induced currents. And they create induced currents when they move vertically through the magnetic field. So at right angles to the magnetic field. So when this one is moving, if this rod is turning in this direction, this guy's moving up. And it's moving up vertically in the magnetic field. This one's moving down. It's moving vertically down in the magnetic field. And it's that vertical up motion and vertical down motion that creates the induced currents, because that's where the motion is perpendicular to the magnetic field. The horizontal motion of those arms. So imagine there's also a motion of this one from the left to the right, and this one from the right towards the left. That's either parallel or opposite the direction of the field lines. That creates no induced current. And so what you see here is the vertical motion that counts in the magnetic field, or the perpendicular to the magnetic field motion that counts, not the parallel or opposite the magnetic field. That doesn't count. And it's sine omega t that picks out the vertical motion. It picks it out over here, and it picks it out over here. So that's sort of technically where the sine omega t comes from. Okay, here's a quiz question. So in this question, you see the rotating loop in a magnetic field. In this case, the magnetic field is horizontal from left to right, and you've got three orientations of the loop. In A, the loop is kind of standing vertically, so it's a plane like this. In B, it's horizontal. And in C, it's somewhere in between. And we're asked to assess or figure out at which orientation do you get the most induced EMF. If this is a rotating loop, at which orientation do you get the most induced EMF? Okay, so maybe I'll answer this one. So in each of these three pictures, there's a different induced EMF in the coil. And that's an example of the fact we discover when you rotate the coil, the rate of change of the flux through the coil is not constant. It's varying in time. There's certain orientations where you get a maximum induced EMF, other moments or orientations where you get zero induced EMF. And then the other locations that are in between those extremes. This one here is in between the extremes. So maybe we'll discount that. The extremes are the loop standing vertically in this horizontal magnetic field lines, and the loop standing plane being horizontal in that magnetic field. The one that has the large rate of change of flux, and hence the one that has the large induced EMF, the one that has the large induced current, is this one here, B. Maybe to help you imagine that again, so the field lines are streaming from the left to the right. Imagine I start with the loop here, and then I'm going to move to the loop here. So I've just moved just a little bit around that horizontal, the loop plane being horizontal. When it's here, if this is the top of the loop, then there's a field line. You can see it on the sketch. There would be a field line going through into the top of the loop. I just got to tip a little bit, and then that field line that's running horizontally would suddenly be coming through the bottom of the loop. So that's actually a big change in field lines. There was, when I had it orientated just like that, there was one going through the top, and I just had to turn a little bit, and then I had one going through the bottom. That's a big change. So that induces a big EMF. The loop being horizontal induces a big EMF in this geometry. This case, A, which is the other possibility perhaps, that's the case where there's no induced EMF at that orientation. If you think about that, supposing the loop was kind of here, just fractionally to the left of vertical, and then it just moved fractionally to the right of vertical. Well, look at the picture. As I do that, as I move from fractionally to the left to fractionally to the right, same number of field lines going through the loop. Still the same 3 field lines that are going through the loop. There's essentially almost no change in flux in this little bit of motion. And so this case here is when you get zero induced EMF, zero induced current. This case here is where you get maximum induced EMF, maximum current. Okay, let's work through a quantitative example of this rotational motion creating induced EMFs. So in this example, little old words on here, but we've got this familiar arrangement, which is our electrical generator based on rotational motion. We're told that the loop has an area of 0.1 meters squared. It's got 1,000 turns. It's 12 ohms, the resistance of the loop and the circuit that it's connected to. And it rotates at 60 revolutions per second in a 0.2 Tesla field. So there's a bunch of information about the loop. It's the N, it's the A, it's the R, and the angular velocity. All those things about the loop. And then it also tells us what the field is, that the loop is immersed in. And we're asked to figure out the induced EMF, maximum induced EMF, maximum induced current, write down equations for the time dependence of the induced EMFs and induced currents. And if I got time, I'll calculate the torque that's needed to rotate the loop in the magnetic field. Okay, I'll work this out on the device that I don't know the name of. Maximum induced EMF. That was the first question, sorry. Let's start again. Of course, what would I do? If I'm sitting in here next Thursday, this is on a test. What am I doing? I'm making a drawing, a sketch of the problem, and I'm annotating the sketch with the things that I know about the problem. So the horizontal lines here, they're going left to right, are the magnetic field. is 0.2 Teslas. Here is a cross-section through the loop. So, you know, maybe the current is coming out up here and going in down here. Here is the area vector. Oh, I've run out of power on the microphone, so I'm going to shout a little bit more. Here's the area vector that represents, that corresponds to the loop. And then over here on the far left, I've written out the various quantities that I know about the loop. So I know its resistance, I know the number of turns, I know the area, and I know the rate at which it's rotating. So it's 12 ohms, 1,000 turns, 0.1 square meter area, and it's rotating. It was 60 complete rotations a second. If you multiply that by 2 pi, that gives you the angular velocity in radians per second. So 60 times 2 pi is 377 radians per second. I wrote down all that information. The maximum magnetic field, maximum induced EMF, so called it epsilon for EMF, subscript m for maximum, is just the product of these 4 quantities. So that's the maximum. Number of turns times the area of the loop times the angular velocity of the loop, all properties of the loop, times the field that the loop is immersed in. So if I plug in all of those numbers into that equation, I know them all. 1,000 for the number of turns, 0.2 Teslas for the magnetic field, 0.1 meters squared for the area of the loop, and finally 377 radians per second for the angular velocity. I got 7,500 volts. And so that's the maximum, what we call the peak, induced EMF that's created by this rotating loop. Look, that's way, way bigger than the translational motion case. This is why this is way, way more practical for generating electrical power, electrical energy, than the translational motion case. Oh, sorry, I went off the screen, didn't I? Okay. The other part of the question was, what is the maximum induced current? So I for current, subscript m for maximum. We can just use Ohm's law for that. The maximum current in Ohm's law is the maximum voltage, the induced EMF maximum, divided by the resistance. This is Ohm's law, V equals IR. All I got to do is divide the 7,500 volts by the 12 ohms resistance of the circuit, and that gives me a current, and that current I got was 625 amps. So again, this is a huge current with rotational motion compared to the tiny currents with translational motion. The second part of the question asked me to write down an expression or a formula for the induced EMF and the induced current versus time as a function of time. So that's a key feature about this electrical generator based on rotational motion, that it's not a constant current and voltage with constant angular motion. It's a time varying current and voltage that has a sinusoidal, a sine wave, sine function time dependence. So let me write those out. So just to stress it, the EMF as a function of time, so put time in parentheses there, is going to be the maximum EMF times sine omega t. And the maximum EMF was 7,500 volts. What am I doing here? the sine function is sine omega, which is 377 times time, times t. And so 7,500 times sine 377 times t is the time dependence of the induced EMF in, this will be in volts. Same sort of thing for the current. So the current, I'm going to write it as lowercase because we normally do that when the current changes with time. It's the maximum current times sine omega t. That maximum current was 625 amps, and it has that same time dependence. Sine of 377 times t for time. And that's in amps. And so those are the expressions for the induced current and the induced voltage versus time. And that's, as I say, is quite different from the translational motion case. Okay, one last thing I'll calculate, which is the torque that you have to apply to rotate the loop. So when I rotate this loop here, I'm transferring energy to the loop. That torque that I'm exerting transfers energy, mechanical energy, kinetic energy into the loop. And it becomes electrical energy, electrical power flowing around the loop. And so that's the way the energy is moving. That's the way the energy is flowing. I'm putting in mechanical kinetic energy, and we're getting out electrical energy, electrical power. So the reason I have to apply a torque, I'm going to call it, this is tau for torque, and the subscript is for my applied torque. I'm just going to worry about the size of it, so I'm going to put the vertical lines around it. The reason I have to apply a torque is because there's a magnetic torque, I'm going to call that tau b, that is trying to oppose the rotation. It's just, remember in the translational case, I had to apply a force to move the rod on the rails because there was a magnetic force that was opposing the motion, and it was created by the induced current in the magnetic field. The same thing is going on here. I have to apply a torque on the loop because there's an opposing magnetic torque that's trying to stop the motion, and that opposing magnetic torque is coming from the fact that there's an induced current in the coil that's in a magnetic field. When you get an induced current in a coil in a magnetic field, that creates a torque on the loop. We actually talked about that back in lecture 11. Remember that? It was like, you know, seems like it was years ago, but it was only 2 weeks ago. We calculated the torque on a current loop in a magnetic field. And we calculated it, we figured it out, and it was this expression here. B is the magnetic field, mu is the magnetic moment of the loop, and that magnetic moment of the loop was just the number of turns of the loop, the area of the loop, times the current in the loop. And so we met this is a lecture 11. All this is completely illegible, but I'm writing it anyway. This is a lecture 11 equation that we derived. And it's telling us that if you need a torque to rotate the loop, because you've got to overcome a magnetic torque that's exerted on the loop, because that loop's carrying a current in a magnetic field, which creates magnetic forces, creates magnetic torques. That torque, we remembered, is equal to the current that's flowing in the loop, times the area of the loop, times the number of turns of the loop, times the magnetic field that it's immersed in. That current is a maximum when this sine theta is 1. So the maximum torque, which is what I'm going to calculate, is when this sine theta function is 1. And all we've got to do to calculate that maximum applied torque is multiply N, A, I, and B. And so if I plug in those numbers, I won't write them all out. You actually get 12,500 newtons meters. That's a big torque too. In an electrical generator, you have to exert, in a power station, to get these big currents, to get these big induced EMFs, you have to exert large torques to rotate the turbines that create the electrical energy, that create the electrical power.